I was just taking a look at the schedule. We've actually got a lot of time left in the, since we meet twice a week, there's a lot of time left in the schedule for reviews. Probably not going to take all that time to review for the final. So we've got both meetings next week that we could use to review. But I'm thinking if we get finished with this week, if we get finished with review for the final this week, then you can have the next week to do whatever you want. You can use it on my class, you can use it on any class. And what I'll do is I'll open up our regular class sessions for the first maybe 15 or 20 minutes to see if anybody's going to show up. That way you can catch me at a particular time outside my office hours and ask any questions, or we can smooth out any problems, whatever. We'll just use it as free time. So that's assuming we get finished with the review this week, and I'm pretty sure we will. Are there any questions? There. Okay. So what I'm going to do, you may notice that things look a little different today. My home computer crashed this morning. We had a power blip, and it messed up my computer. So I've just got it back on now, but I haven't fixed the camera yet. So I'm still on my laptop. I did manage to transfer the 4K camera over from my office computer to the laptop. So we should have pretty good resolution, and the video recording should be reasonably legible after processing. It's just I can't get the there. That looks a little bit better. Okay. So what I want to do to review is go over some major concepts, of course, and work some particular problems. That's where the concepts are actually show their worth. And where you really learn chemistry is when you work problems. Any chemist that can't work problems is not a chemist. So let me see. Do I have it open yet? Yeah, there it is. Okay, so I'm going to share. Where is it? Here it is. I'm going to share that document. All I have to do is find it again. Here. There we go. And so I can see what's going on. This laptop has a much smaller screen. So what I'm going to do is collapse the I can't remember what you call them. Collapse the list of attendees on the right. There, now I can see everything. All right. Now that's not where we're going to start. That's just where I was fumbling around looking for things. But we're going to take everyone in the list. This is a review. I put this document together over a year ago for a previous Chem 101 class. And it accompanied the videos, and you may still find these videos in Blackboard for fall 2020. There were 2 of them. So in class, it took me 2 class periods to complete the review. So let's see how we can do. There we go. Scroll up a little bit. And I wonder if I can make that bigger. and then scoot it sideways a little bit. Yeah, I think I can see it better. And it should show up better in the recording also. Okay, some of these ideas, you've been using them for the whole semester, so they probably seem antiquated. But this, we're just going to get our feet wet and move into it as we go. All right, for number one, which of the following is an example of a quantitative observation? In the sciences, there are two types of observation. There's the qualitative and the quantitative. All right. Qualitative is a general description. You could say the solution is blue. All right. So you have a blue solution. The quantitative equivalent of that would be this solution absorbs light, maximum absorbance, wavelength, max absorbance would be, say, in the neighborhood of 650 nanometers. This is qualitative description, and this is quantitative. It always has a number, and more often than not, a unit of measure. That's the difference. So when we're looking at this question, the piece of metal is longer than the piece of wood. That's a qualitative description. It doesn't say how much longer. It doesn't say anything about the lengths of either one. So it can't be quantitative. Solution 1 is darker than solution 2. That's qualitative also. This one is the one I just mentioned. Liquid in the beaker is blue. The temperature of the liquid is 60 degrees Celsius. That's your quantitative observation. You have a definite number. Rather than say the liquid is hot, we say it's exactly 60 degrees Celsius. That's quantitative. So that makes D the answer. I'm pretty sure this document is in Blackboard. I'll check to be sure after we're finished today. But I created it specifically to go along with the video. The two videos, actually. So it should be in Blackboard, but I'll check to be sure. Now, the numbering sequence is not going to be right. As I threw it together pretty quick, and I did it in such a way that the list numbering system in Word is not very user-friendly. So it skips around. But I'll use the numbers that are in the document on the board here. Which of the following has a different value on the moon compared to the Earth? Right. So this is a question referencing absolutes versus relative. Now, in these terms, we know that mass is absolute. Mass references the inertia of an object. And that is independent of all reference systems in the universe, except for the ones that are relativistic, they say. They're very, very large masses, like around a black hole. Things are not quite, they don't fit with Newtonian physics. But in that world, mass is an absolute. So it's going to be the same on the Earth as it is on the moon. Same mass. Weight, however, is a measure of force, and that is relative to the size of the object that you're close to. In this case, if I'm close to the Earth, on the surface of the Earth, I'd be about 200 pounds. But on the surface of the moon, I'd be about 33, 35 pounds, something like that. So those two have different values. Now, which one has a different value on the moon than the Earth? Well, weight does. Time also is a constant. In other words, 1 second on the moon is a second on the Earth. Moles, that's just counting. That's just numbers of stuff. So it doesn't matter where you are. A mole's the same. Mole's a mole. So the weight is the only one that's different on the moon relative to the Earth. Now they're related, right? If you know the mass, and you know the acceleration under which that mass is being forced, you get the weight, right? And on the surface of the Earth, mass is whatever it happens to be, and this has a special symbol. It's called G. That's the acceleration due to gravity. You didn't think that the gravity causes acceleration. Well, if you're standing on the surface of the Earth, yeah, it does. And if you are at an altitude and you drop, the force applied to your body is going to be relative to the acceleration of gravity, and you're going to accelerate at a certain rate. And when you hit the ground, there's going to be a certain amount of force applied to your body. And if it's sufficiently large, it will kill you. So this particular value is 9.8 meters per second squared. On the moon, it'll be 1/6 of that. And that way, you get 1/6 of the mass, of the weight on the moon as you do on the Earth. Okay, that's probably more than you wanted to hear about that topic. So let's look at number 4. All the following characteristics of nonmetals. All of the following are characteristics of nonmetals, except. Okay, so what do we know about metals and nonmetals? Well, let's see. Their appearance, nonmetals are usually dull, and metals are usually shiny if they're polished. Nonmetals are poor conductors of heat, right here. Metals are good conductors of heat. So that's a characteristic of a nonmetal. That's not our answer, because we're looking for the exception. Nonmetals tend to be brittle. If they're solids, right? But we know that nonmetals come in 3 different phases. There are gas nonmetals, like the noble gases, for instance. There are liquid nonmetals, like bromine. There are solid nonmetals, like, I don't know, silicon. If you've ever seen a pure ingot of silicon, it's amazing to look at. In fact, it has sort of a shine to it, but it doesn't have a metallic luster. Well, silicon's a bad example because it's a metalloid. It's very close to the metal side. So let's pick something else. How about sulfur? Yeah, solid sulfur is definitely dull. And the solid brick of sulfur is easy. I mean, it breaks easily. It's very brittle. Ductile. Ductility is the characteristic of an element or a substance that allows it to be drawn into thin wires. It's ductile. So that's how, and that's characteristic of metals, not nonmetals. So actually, that's your answer. The dull appearance, of course, tend to gain electrons in chemical reactions. Those are definitely nonmetals. Metals give up electrons. nonmetals gain electrons. So C is the answer. Ductile is not characteristic of nonmetals. All right. Now we'll skip to 7. Let's see, did I lose somebody? Sarah Brooke, Tierson. Yeah, I lost somebody. Jordan? Yeah, lost Jordan. Okay, 7. The correct name for FeO. Right, so you go back to your nomenclature rules. Right. What type compound is this? 1, 2, or 3? Well, there's a metal and a nonmetal. So that means it's not type 3. It's either type 1 or type 2. So what's the difference between the two? Type 1s, all the metals are fixed charge, can't be anything else but that. Type 2, the metal is capable of 2 or more different charges depending on the compound. Right? And those are, by and large, transition metals. Right? They occupy this part of the table. Now we'll sort of slide into this part for also. Right? So anything to the right and not quite into nonmetals is fair game for type 2 compounds. So how do you name the compound? Well, you need iron, of course, and you need oxide, right? IDE. Now you need to say, what is the charge on the iron? Type 2 compound. Well, we have to work from something. And oxygen we take as -2. So that means iron has to be +2. That's the only possibility because there's only one of them. Right? So the answer to that one is D. Iron 2 oxide. How about 8? The correct name for Ca2+. First of all, what is that? Well, it's derived from the element calcium, correct? But it's not a neutral atom, it's an ion. Right? So that lets out A. It's one of the following, B, C, D, or E. But what is it about calcium that's unique? It is an alkaline earth. It's in the second group. Every member of that group has a 2+ charge. So that means we don't have to say what the charge is. There's no need for that. So we don't say calcium 1 or calcium 2. We definitely don't say monocalcium. If you say calcium, there's only one of them. So it is the calcium ion. That's it. We don't need to be redundant. If we said calcium 2 ion, that would be redundant because calcium can only be 2+. Calcium ion is the answer to number 8. All right. Let's see. Are these going to be in sequence? All right. So here we have sort of a graphic of different types of possibly mixtures, but maybe pure elements. We don't know yet. Notice here we have a box where the particles are spread way apart. Same thing for this one. Particles spread way apart. We can assume that those are gases. let's see. This is going to be a series of, so we'll start with 12. 13 and 14, I think, look at the same. Now, see, here we go. Questions 13 to 15, well, they're kind of out of whack. Starts with 12. So you have to sort of interpret this document. Okay, for 12 here, we're going to look let's say A, B, C, D, and E. So A appears to be a gas, as does C. All right. What about B? What does it look like? Looks to me like a solid. And it looks like the structure is regular. Right? So B, we can take as a solid. How about D? Well, D doesn't have a regular structure. It also has two different shades of particles. So it's obviously a mixture. As A is a mixture also, we might as well put that in there. A is a mixture. Okay. And D is a mixture. Okay. But it looks to me like it's a liquid, right? Because there's no regular order to it at all. But the particles are still close together, which is characteristic of liquids versus solids. The densities are very close together. Usually liquids are a little less dense, not always, but usually. But the particles are able to slide past one another very easily. That's why liquids require a vessel. They take the shape of the vessel, but they still retain their own volume. Whereas a solid is regular in structure, and it retains its own shape and volume. Okay. How about E? What is E? E is probably a solution. It's definitely a mixture. Yeah, it's definitely a mixture. But it's probably a solution. We don't really know, but I don't think the particles are far enough apart. We'll just say it's a mixture, and we're not sure whether it's a solution or on its way to a gas. I don't think the particles are far enough away from each other to be a gas. So how about B? B is pure, right? B is an element. There's only one type of particle in there. And it's represented by a single sphere, which we take to be an atom. And the reason I say that is if you look at these other, you see combinations of these particles, which implies compounds. Okay? C is a compound. And it's a pure compound. There's only one type in there. It's a gas and it's a pure compound. Okay, element, mixture, mixture. All right, so now that we've got them characterized, let's look at the question. Which best represents a homogeneous mixture of two elements? Right? If it's a compound, you can't call it that. Right? That's a compound. This has compounds in it. This is not a mixture. This has no compounds in it. So it's also a homogeneous mixture. Right? How about this one? Is that homogeneous? No. You can just stare at one part of it, right? And compare that to another part of it, and it doesn't have the same composition of each element. So A is the homogeneous mixture, right? So for 12, A is the answer. Why? Because mixtures of elements in a gas are always homogeneous. They are always solutions. How about 13? Which best represents a homogeneous mixture of an element and a compound? All right. So we need, for 13, we need an element and a compound. Right. So these two go together. 13 means homogeneous mixture of an element and a compound. Where do you have an element and a compound? Those are all elements. That's a pure element. These are all compounds. These are all elements. So really, by process of elimination, E is the only one. The square is an element. The two circles, the clear and the shaded one, are part of a compound. And it looks like they're regularly arranged, like there, change, there, change, there, change. That's a regular arrangement. So E is 13. Those two together. Let's see, is 14 another one? Yep. Which best represents a solid element? All right, we have to have an element. Right? This is not it. That's a mixture. That's not an element. That's got an element in it, but it's not pure. And it's not solid either. So really, B is the only one. B is a solid element. Okay? All right. Let's see. I got till 3:45. Got another hour and 15 minutes. All right. So we we skipped from 14 to 28. Be sure I'm still on camera there. So 28. All of the following are in aqueous solutions. That's given. Each one of these is in aqueous solution. Which is incorrectly named? Right? In aqueous solution, notice A through E, they all start with a hydrogen. Right? Those are the hydrogens that dissociate from these compounds and produce acidic solutions. So that's why they're all named acid, 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 acid. So that characteristic of each compound is true for every one. So we have to look at this part of the name here in order to see if it corresponds to the compound as written, or if the compound is written incorrectly compared to the name. They have to match. Okay? So, how about A? If we write this compound, what do we know about the rules for naming acids? If there's an oxygen in the molecule, you do not say hydro. You just take the part with the oxygen. It's always going to be a polyatomic. So you go to the polyatomic name. What is the polyatomic name for SO4? Sulfate. And when you make an acid out, when you dissolve it in water, then the H's become X. So this would be sulfuric acid. Okay, that one's true. How about this one?
Oh, by the way.
Right? We don't say hydro for this one either. So we look for that. What is that? That's the carbonate. The carbonate ion. So when we make an acid out of it, dissolve it in water, 8 becomes X, carbonic acid. How about C? H3PO4. Right? There's another one we don't say hydro. PO4 is phosphate. So we sort of modify the rule. Instead of saying phosphic, we say phosphoric. Okay, well, that one's true. So far, so good. How about D? HCl. No oxygen. So we're going to start it with hydro. And then you look for Cl, which is, what would it be if it were not dissolved in water? It would be hydrogen chloride. And ides still become X. Hydrochloric acid. Okay, that was true. It looks like process of elimination, the last one, HCN. No oxygen here, so we start that one with hydro. But CN is a polyatomic, cyanide. So I becomes X. Hydro. Cyanic acid. That's the wrong one. That one is false. It should be hydrocyanic acid. All right. Okay. There. Oh boy, we get the targets now. 35. Let's see. Okay. 35 is alone referencing these targets. All right, the question is, which of the following figures represents a result having low precision? Right? Remember the different definitions: accuracy, and precision. Right? Accuracy is close to the true value. Or in lieu of the true value, the accepted value. Whereas precision refers to grouping of measurements. Right? Close grouping. So you can't say anything about precision unless you have at least two measurements. Whereas with accuracy, you can say, okay, yeah, it's either close to the accepted value or it's not. But with precision, you need two or more. In this case, we got 5 for each one of those targets. So which of the following represents a low precision? Not close grouping. Right? That would be number 1. Right? This one. Because these are close together. That's high precision. This one's high precision. Now, number 2 is high precision but low accuracy. It's way far away from the bullseye. But number 3 is both precise and accurate. Now, the only one that we're not showing in here is one that's not precise but accurate. 1 almost gets there. If those were evenly spaced around the bullseye but spread apart, then their average would be right on the bullseye, and that would be accurate. Okay, so let's shift down to number 38 now. We go from 35 to 38. Okay. The amount of uncertainty in a measured quantity is determined by. Okay, this is a practical question. what is it that determines the uncertainty? And every measurement has an uncertainty. You can never be sure, absolutely sure, that your measurement is the true value. So you have to deal with the uncertainty in some form or fashion. But what causes uncertainty? Well, when a measurement is made, well, it used to be only measurements were made by a person and an instrument. It may be something as simple as a meter stick. Now we have instruments that will do the measurement for you, right? We have several of them on the surface of Mars right now, but they're still connected to humans in some form or fashion. It's just what we've done is we've minimized, out of necessity, minimized the human element in that measurement, because we're not ready to send humans to Mars yet. So we're using robotic crafts. So that being said, we modify, rather than saying the human or person, we just say the observer. So in that case, it could be a robotic system that's observing, and then the instrument it's using is the other part of the equation. So when you make an observation, the instrument could be very accurate, right? And very precise for that matter. But the user could be incompetent, right? If someone has a $250,000 instrument and they don't know how to use it, they're going to come up with bad results, right? I used to have a $250,000 instrument sitting in a special room with its own air conditioning because it generated a lot of heat, and it was more stable. If we could keep the temperature stable, it would work better. But anybody that went in to use that instrument, if they didn't know what they were doing, they would get garbage. Their values would be worthless. And not to name names, but we had several technicians that were incompetent. So I tried to keep them away from that instrument. Anyway, those are the two factors: the observer and the instrument are the limiting factors. So both the skill of the observer and the limitations of the measuring instrument are factors in determining the amount of uncertainty in a measured quantity. So C is the answer to 38. (41). Okay, which of the following are incorrectly paired? All right, for this one, we're taking the symbol for an element and we're trying to match it up with its group name. Right? Some of the groups have names. So how about calcium? Is the calcium an alkaline earth metal? As a matter of fact, it is. Why? Because it comes from the second column, and all of those are alkaline earths. Okay, that one's true. How about V? Where's V? What is V? V is vanadium. V is right here. It's a transition metal. That one is also named correctly. How about Cl? That's chlorine, correct? Chlorine's over here. It's in the group of halogens. That's true also. How about H? H is way over here. And it says H is a noble gas. I don't think so. Noble gases are over here. There are several people, including Hindenburg himself, who wish that hydrogen had been a noble gas. Otherwise, the Hindenburg airship would not have burned to the ground. But as it was, hydrogen actually is in a class by itself. It doesn't belong to any group. And of course, U is uranium. It's way down here. And it's one of the actinides. Why do we call it actinide? Because the first member of the group is here, actinium. Uranium is an actinide. Okay, so D is the answer to 41. 46. Okay. The boiling of water is a, okay, now we're looking, if you look at the questions, you can see what they're getting at. Physical change or chemical change? That's the first part of the answer. Then there's a why to it. So the boiling of water, we know what? That is a physical change. No two ways about it. So that means C, D, and E, they're out. Physical change, because what? Because water merely disappears. Okay, maybe. Or because the gaseous water is chemically the same as the liquid. That's the key. The water that's in the gas phase now has exactly the same chemical identity as the water that was liquid before it boiled. In fact, A is partly true, because water merely disappears. Well, no, that can't be it. And I'll give you an example. B is the answer. But A is not the answer, because I'll give you one example where the water disappears, but it's not a physical change. There's water. This is the simplest way to put it. Say we have a little bit of acid in there. Not much, just enough to make it conductive. Then we drop a 9-volt battery in it. So they have a little nub here, and they have a big one here, like that. I can't remember which is negative, which is positive. Anyway, when you drop that battery in this slightly conductive water, you start to get bubbles. If you leave it there long enough, the level of water goes down. The water is disappearing. But it's due to a chemical change, because you're producing hydrogen gas and oxygen gas. Right? So A cannot be correct just because the water disappears. We can make it disappear by chemical action too. All right, that was 46. Let's see, what number are we jumping to this time? 54. Okay, fill in the table. All right, so we have, see, I'm going to start from the right. Net charge. All right, and then next we have number of electrons. And then next to that, we have number of neutrons. And then we have number of protons. And then we have symbol. There. Okay, we're given this one, 206 SN. What is SN? SN is 10. Okay? If you know the element and you have a periodic table, which is valid to have in any exam that you take with me, then all you have to do is know where 10 is. Find 10. It's right over here. Then you can find that 50 is the atomic number. Right? So the number of protons is 50. All right? Now, what's this number right here? That's the mass number. The mass number is protons plus neutrons. So how do you get neutrons? Well, if 50 of them are protons, then the rest of them are neutrons. So 50 from 206, which is 156, correct? Okay. How many electrons do you have? To find out how many electrons, you look to see, does this thing have a charge? Nope, no charge. It's neutral. That means protons, electrons are equal. All right? And we just said there's no charge. So that completes the table for this one. How about the next one? Well, we're given 35 protons and 40 neutrons and 36 electrons. Okay? We can determine the charge right now, can't we? It's got one less proton than electron, which means the balance is -1. Right? So this is a 1 minus. How about the symbol? The symbol, we just had 35 protons. That means the atomic number is 35, and we just go across here until we find it. Bromine. So that one is Br, and it has a -1 charge. Right? How about, well, we weren't writing it here, so we don't have to write 35. You can write 35 if you want to. But up here, we need 35 plus 40 to get the mass number, 75. So that would be the minimum for expressing that information, this one right here. Okay, what else do we have? Fe2 plus. There we go. Okay. Now, well, what's the number of protons? Well, we'll look it up, right? Find iron. It's right here. 26. So we have 26 protons. But we don't know how many neutrons because, well, not from this information, because it has isotopes, right? So fortunately, they're given to us. 29 neutrons. So that means, what's the mass number? Well, you don't have to put it in there because it's given to you. But if we needed to know, it would be 55, correct? How about the number of electrons? If the balance is shifted toward the positive, that means we have fewer electrons than protons. How many fewer? 2. So we have fewer electrons in this one. 24 electrons. And the charge is 2 plus. Okay. Oh, that was given to us also. Okay. Any problems with that? All right. That was 54. And we're coming up on, oh, wait a minute. It's not even 3 o'clock yet. We got till 3:45. I wonder, we might even, well, let me jump the gun. We don't have to rush, in other words. We can come back and finish this on Wednesday. Let's see, let's switch. There we go. Okay, name the following compounds. All right, for this one, well, we did one earlier where it was multiple choice, but now we actually have to write the name. So 55 through 6, 7, 8, 9, yeah, 61. 55, 56, 57, 58, 59, 60, and 61. Okay, 55. CF4. What kind of compound is that? 1, 2, or 3? Type 1, 2, type 3. Type 3. Carbon and fluorine are both nonmetals. Okay, which means we borrow from the ionic type 1, type 2 compounds for our naming convention, but we don't have to say what the charge is. We just have to say how many elements are there in the compound. Remember, if there's only one for the first element, you never say mono. You just say carbon. And then we use our Greek prefixes for the number. 4 is tetra. And then fluoride, carbon tetrafluoride. Okay, how about this one? All right, we have a metal, and hydrogen is technically a nonmetal. But we only have one of them. So in this case, we use the IDE ending for hydrogen. This is the positive, this is the cation, this is the anion. This is one of those cases where hydrogen takes on a negative charge. It's usually a positive charge. But in this case, it's lithium hydride. The hydrides are an interesting group of metal compounds. And in fact, that's one of the approaches to storing hydrogen for use in electric vehicles is by making it into a hydride. So you pump the hydrogen in to this metal matrix, and the hydrogen bonds to the metal. But it's not a very strong bond. And you pump it in under pressure, only the metal absorbs a lot of that hydrogen, so the final pressure is not very high. It makes it safer. And then once you open the valve, when you want to use it, it comes out at a slow pace, just fast enough to power your fuel cells. That's not the only place it's used, lithium hydride. It can be used other places. That's just one example. All right, let's do 57. COI2. CO2. Okay, what type of compound is this? Well, you got a metal and a nonmetal. So it's either a 1 or a 2. Cobalt comes from the transition metal, so it's a type 2. So now you need to say cobalt. Iodide. What's the charge on cobalt? Well, each one of these is -1. So that means you have 2 minuses here that have to be balanced with a 2 plus, like that. Okay, 58. AgCl. This is similar to that one. Metal, nonmetal. Silver is a transition metal, but silver only has 1 charge, plus 1 charge. So technically, you would say silver chloride. And you would be correct. But I tried to simplify things where the rules are concerned in this course and say, okay, silver is a transition metal. If you want to, just say it has a +1 charge. If you're going to advance in chemistry, you may want to forget that rule, right? Because technically, the type 1, type 2, type 3 rule says that silver can only be 1 charge, so it's really type 1. And that's why when I talk about silver chloride, I never say silver 1 chloride. I just always say silver chloride. Okay, HNO3, HNO3, AQ. That means, well, along with this and that, this is an acid. You got to name it acid convention. So what's NO3? It's nitrate. It's got an oxygen, which means we don't say hydro. We just say 8 becomes ic. This is nitric acid. How about 60? N2O5. N2O5. 2 nonmetals, type 3 compound. So we got 2 nitrogens. Dinitrogen, pentoxide. We drop the A on the end. 2 vowels together is kind of hard to deal with. That just doesn't sound right. So it's dinitrogen pentoxide. And the last one, NH4, NO3. NH4, NO3. Right? Type 1 compound. Fixed charges. Why? Because these polyatomic ions always come in 1 charge. If you change something about the polyatomic, then it might be a different charge, but it doesn't have to be. So nitrate is -1 charge. Ammonium is a +1 charge. So you just say what they are, just like they were a type 1 compound. And the polyatomic ions give you the name that's unmodified. Ammonium nitrate. Right? That's the infamous oxidizer for the fuel oil bomb that destroyed the Murrah building in, where was it? Kansas City, I think. Anyway, those are named compounds. Oh, now we got to write the formula for them. Got to go the other direction. Okay. 62 through 67. All right. So magnesium hydroxide. Magnesium hydroxide. Magnesium, of course. What type of compound is this? It's type 1. You've got a metal, but it's not a transition metal. It only has 1 charge. It's an alkaline earth. Magnesium is a +2 charge. Hydroxide is a polyatomic ion with a -1 charge only. So we need 2 of them. But where do you put the 2? Right. Polyatomics cannot be split. If you put the 2 here, you're saying there are 2 hydrogens and 1 oxygen. That's water. This is hydroxide taken twice. 63, dibromine heptoxide. Okay. What type is this? Non-metal? Non-metal. Type 3 compound. Of course, these prefixes give it away also. So 2 bromines and hept. What's hept? 7. 7 oxygens. Br2O7. How about manganese 4 oxide? Okay. Manganese oxide. Oxygen has a 2- charge. This one has a 4+ charge. So if this is 2-, how are you going to balance 4+? You need 2 of these. Right? MnO2 is how you would write that. Okay. 65. Sulfurous acid. All right. We know it's going to be aqueous because it's an acid. We also know it's going to have hydrogen out here. But where does the sulfurous come from? Notice, with no hydro, that means there's got to be oxygen in there somewhere. So this one is derived from a polyatomic ion, eight becomes ick, and ite becomes us. So what is sulfite? We know sulfate is SO4. Sulfite is SO3. But it still has a 2- charge, just like sulfate. That means we need 2 hydrogens because protons have a plus charge. So there you go, in aqueous solution. (66) Acetic acid. All right. This one's aqueous also. And there's oxygen in that polyatomic. We need to know, what is ick derived from? The polyatomic that ends in 8. Acetate. The acetate is C2H3O2-. So we need 1 proton. And there's acetic acid. Last one, nitrous acid. Aqueous. Okay, like this one, us comes from ite, so it's nitrite. So nitrate is O3, nitrite is O2. NO2 has the same charge, -1, so that means only 1 hydrogen is needed. And there's your nitrous acid. All right. So how are we doing? 107. We skipped from 67 to 107. There we go. There. All right, 107. A manometer is attached to a sample of gas. So what does a manometer do? Well, we know what a barometer does. It just measures air pressure. A manometer measures the pressure of a trapped gas. How much pressure is applied by that gas inside the vessel? Okay. The sample of gas occupies a volume of 2.34 liters. And it's attached to a manometer that's open to the atmosphere. So that means that atmospheric pressure is bearing down on whatever's in this tube. And what's in the tube is mercury. The mercury level in the arm of the manometer attached to the gas sample here is 24.3 torr lower than that of the arm open to the atmosphere. So over here, that difference is 24.3 torr. Millimeters of mercury. All right? So what does that mean? That means the pressure inside the vessel is greater than the atmospheric pressure. What's the pressure of the sample of the gas? What else do we need? We need to know what's bearing down right here. Right? We've got this difference in mercury height. So what's the pressure here? Well, it says 1.23 atmospheres. 1.23 atmospheres. Right? So what do we need to do? We need to add this one to that one. Not yet. They're different units. You can't add apples and oranges. So let's convert this one to torr. Right? Okay. 1.23 atmospheres. We need to convert that to torr. Right? So torr's up here, atmosphere down here. How many torr in an atmosphere? 760. All right. So let's find out how many torr that is equivalent to. See, three significant figures. Let's keep one. 934.8. Let me be sure I did that right. 760, 1.23 times. Yeah, 934.8. So now we can say this pressure plus this difference, right? Because that added height over here is pushing against the gas, but the gas is pushing back hard enough so it balances both the atmospheric and the difference in height of the mercury. So 934.8 plus 24.3 would be 11, 9, 5, 9. Now, and technically, we could only keep 3 here anyway. So I'm going to have to round it to 3, 959. So is that 1? Yeah, there it is. 959 torr. All right, that was 107. Okay. Oh, not right now. 110. There we go. Complete the following. Because real gas particles have attraction for one another, so whatever the A through E is, it has to follow directly from that statement. Because real gas particles have attraction for one another. Real gases act most ideally at standard temperature and pressure. Is that true? The key there is not just real gases, and standard temperature and pressure is most ideally. So standard temperature and pressure does not guarantee the most ideal conditions. What does? High temperature and low pressure. Low pressure means there are very few molecules in there to interact with one another. And high temperature means if they do smack into each other, there's enough energy to overcome any intermolecular attractions that may exist. So high temperature and low pressure is the ideal. So still, so that one is false. How about B? We assume gas particles have negligible or zero volume. Because real gas particles have attraction for one another, does that have anything to do with their volume? You could stretch it, I suppose, but there's no direct involvement of the volume of a gas particle in terms of the attraction from one to the other. Any size particle, whether it's vanishingly small or assumed to be zero, could still have attraction between the particles. Just because we say there's no volume is not a reason the reason gas particles have attraction to one another is not sufficient to cause us to assume no volume. So I would tend to say B is false. C, 1 mole of an ideal gas at standard temperature and pressure has a volume of 22.4 liters. That has absolutely nothing to do with the attraction. It's going to be that way regardless. It's only based upon the formula, PV equals nRT. D, real gases act more ideally at higher temperature and low pressure. D is true. So C is false and D is true. High temperature, low pressure. Okay, looks like 120, 21, 22, and 23 are together. All right, so what are the conditions first? We're going to get to 20 through 23. What are the conditions? A gas in a 1 liter bulb at standard temperature and pressure. So we've got a 1 liter bulb. .0 liter at standard temperature. For gases, standard temperature is 0 degrees. And pressure, 1 atmosphere. Okay. Is connected via valve to another bulb that's a vacuum. So we've got to connect this to another bulb, and it doesn't say what volume it is. Probably doesn't matter. So this is a vacuum. Okay, so I suspect we're going to open the valve. When the valve is opened, what is true about the value of delta H? Well, the key here is standard temperature and pressure. There's no change in delta H. Delta H is 0 for constant temperature, right? So 120, delta H is 0. 121. How about Q? Well, actually, this is where delta H and Q definitely agree. Plus, the pressure is constant. So delta H is equal to Q. Right? You can never measure heat transfer without a change in temperature. It's the only way. What's true about the value of W? What is W? W is work, right? Was there any work done? No, the gas just migrated. And there's no expanding piston. There's no way to extract a force through a distance, right? Force moving through a distance required for work. And that didn't happen. So that's equal to 0. How about delta E? What's delta E? Delta E equals internal energy, change internal energy, which is equal to what? Q plus W. Both of those are 0, so delta E has to be 0 too. So all these guys are 0 for that particular experiment. All right, 136 now. Okay, choose the correct equation for the standard enthalpy of formation of CO, gas. GR indicates graphite. Okay. How do we write the standard, how do we write the formation equation for a compound? You always start with the compound on the right-hand side because you're forming it. It's a product. Right? And this is in standard state conditions. So when we form that, what does it have to come from? It has to come from elements in their standard state. So what's the standard state for carbon? Graphite. Okay. And how about oxygen? Oxygen is diatomic gas. Right? So the rule is that is 1 mole and you can't change it. You have to deal with it on the reactant side. So 1 carbon, that's good. 2 oxygens, 1 oxygen, we need 1/2. All right. Delta H of formation, that doesn't change for any of them, it looks like. Minus 110.5. Okay, so this is an exothermic process. So which one matches? Well, let's see. We need all these that say 2 over here. They're wrong. It's always 1 mole of product. So how about this one? There's only 1 oxygen atom. Won't work. It's got to be standard state conditions. Okay. So that one's good. This one's good. That C. C is the best answer. There you go. All right. How about this one? Uh, 142. Nitric acid was first prepared 1,200 years ago by heating naturally occurring sodium nitrate, saltpeter, with sulfuric acid. That's interesting. So the ancients knew about sulfuric acid before they knew about nitric acid. And what was produced from that reaction was sodium bisulfate. You collect the vapors of HNO3 produced. Calculate delta H for this reaction. All right. Oh, and there's the reaction given to you. That was nice of them. So when you react sodium saltpeter with sulfuric acid, you get sodium hydrogen sulfate plus nitric acid as a gas. Okay. So how do we calculate the delta H for this reaction? Here we go. What's the rule? In order to calculate the delta H under standard conditions, which is what's asked for, delta H 0 for a reaction, we can use the heats of formation for each of the products and the reactants. Remember that formula? Delta H equals the sum of the delta H's of formation for the products minus the sum of the delta H's of formation for the reactants. Okay? Now, why did I put that N there? Because the N is the number of moles from the balanced equation for each one of them. So if we had product here, if we had more than one of those, we'd need 2, 3, 4 up here. But since everything is 1 to 1 to 1, N is 1 all the way through. So all we need to do is take that value plus this value and subtract this value and subtract that value. Right? So what is sodium hydrogen sulfate formation? Minus 1125.5. Minus 1125.5 in kilojoules. And then we have HNO3 minus 135.1. And then we subtract the reactants. So sodium nitrate, saltpeter, minus 467.8. And then we have sulfuric acid, which is minus 814. There we go. That was the hard part. Now we just crunch the numbers. So 1125.5 negative, and then 135.1 subtract. And then these are both going to be positive, right? A negative times a negative, negative times negative. 467.8 and 814 is 21.2. Actually 4. 21.20. Kilojoules. Check, make sure I'm right there. Yep. And that's a positive value. So this is an endothermic reaction. Right there. Okay. What's next? 145. There we go. Okay. The force between two bodies having identical electric charges. Oh, this is basically a definition. The force between two bodies having identical electric charges. So it doesn't say what they are, it just says they have to be the same. So it could be negative, negative, or it could be positive, positive. Okay? Identical electric charges is a force of repulsion. Well, yeah, that's right. Like charges repel one another. Is a force of repulsion if the charges are negative and one of attraction if okay. No, I don't think so. It don't work that way. It increases as the bodies are moved. The force between the bodies increases as the bodies are moved further apart. No, it decreases. Right? My mind's gone blank. D, the force between two bodies of identical electric charge is independent of the distance between them. No, that's not right. It decreases with the distance between them. In fact, it decreases as the square of the distance between them and is directly proportional to the distance between them. No, it doesn't increase at a rate. As they get further apart, it doesn't increase, it decreases. All right, so really there's only one right answer, and that's A. There you go. Coulomb's law. That's what I couldn't remember. Coulomb's law. So the force between the particles is equal to Coulomb's constant, whatever it happens to be, and the charge. Now this is a different use of Q. In physics, Q is a charge. Right? Q1 times Q2 over R squared. The distance between them, R squared. So the value of this force is going to be negative if they're opposite charges, and it's going to be positive if they're the same charge. And a positive force means they repel one another. A negative force means they attract. Okay, that was 145. Okay, now we're getting serious. Which of the following molecules has no dipole moment? We have to remember what a dipole moment is. When we're talking about the molecule, the dipole moment is the overall distribution of electron density. So if the electron density over the whole molecule is uniform, you have no dipole moment for the molecule. And there are two things that speak to that issue. One is do the bonds have dipoles? And the second one is molecular geometry. Okay, so let's look at an example. Carbon dioxide. So how are we going to deal with this? You got to draw the Lewis dot structure. Right? So you know how to do that. Valence electrons. There are 4 for carbon, and there are 6 each for oxygen, which is 12. 16. So now we have carbon and an oxygen and an oxygen. So that's 2, 4, 12. 2, 4, 6, 8, 10, 12. So we used up all our electrons. That's what this was, electrons. But we don't have octets yet. So we've got to make an octet. So if we put one of these over here and one of these over here, we have this, like that. Okay. Now we got the, what's the structure for this molecule? BSEPR. 2 groups always means linear. So it is written correctly, like that. Now, do we have a dipole in this molecule? Well, we have one going this way, and we have one going this way. Equal and opposite. They cancel one another out. So this one has no dipole moment. All right. E can't be right because that says none. We found one that is no dipole moment. If we find one we have to do the other 2 to be sure that they're not also. So ammonia, right? Nitrogen is 5 valence electrons. Hydrogen is 3, so we have 8. So we have nitrogen, 3 hydrogens, 2, 4, 6. That means we need 2 more. Right there. Okay. What is the electronic geometry of this molecule? 4 groups, tetrahedral. Okay. Now we cover that up and say, all right, so what's the molecular geometry? It's a trigonal pyramid. Okay, so it's going to look something like this. Hydrogen in the back, hydrogen out here, hydrogen out here, and we form this triangle in the base. And then we have a lone pair up here. Okay, which one's more electronegative? Nitrogen is slightly more electronegative. Like that. Plus you got the lone pair. Right? So this is polar. How about C? Oh, that's water. We know what water is. We don't even have to do all that mumbo jumbo. Water looks like this. And overall, since it's bent, water is polar also, which means it has a dipole moment. Dipole, dipole, no dipole. So A is the only answer that is correct. It's not all of them. It's not none of them. So it has to be A. All right. Let's move this back a little bit. There we go. 152. Let's see, we're coming up on 338. Let me see, what page is this? 8. How many pages are actually in this thing? 14? So that means we have 6 more pages. Let me see what's left on page 8. Choose the molecule with the strongest bond. All right. I can remember doing this one in the previous review, I think. So these are all halogens, correct? It's what's known as a homologous series. We're only changing one thing. All are equal. I think we can count that one out right off the bat. F2. So I'm going to write it like this. Cl. Bromine. And iodine. Okay. What are 2 factors that contribute to the strength of a bond? Especially when they're diatomic like this. It really simplifies things. The 2 factors that determine the strength of a bond are, 1, electronegativity, is how strong is the pull, and 2, size. Okay, so if we were dependent on size only, iodine is a huge atom. It puts the nuclei very far apart, spreads out the electron density in the bonding orbitals. This is the weakest one. And this one gets stronger, and this one gets stronger. What happens? When we get to this one, the trend reverses. It's more electronegative, yeah. And the atoms are very close together. But the fluorines draw so strongly on electrons, they draw electrons away from the bond, which weakens the bond. So electronegativity can be thought of in 2 different terms. Electrostatics, right? Actually just the pull, and the electron density. So this should be the strongest one right here. When you get to very, very small atoms, like the fluorine atom, then what you get, and here's another thing that creeps in. The nucleus, right? In these, you have some core electrons that are shielding the nuclei from each other. So you get this covalent bond formed, and it's more stable for these big ones, for this big one. Not for these, but for this one. As you get the nuclei closer together, you get those protons so close together, they push apart. In fact, I think that's the major effect. You get the smaller atoms, there's no shielding, and the protons push apart. Let's see, fluorine's got 9. So you got 9 protons in here and 9 protons there. And they repel one another. So you get so close with the fluorine that this repulsion is the problem. So it wasn't so much electronegativity as it was repulsion due to the size. All right. Let's see. In the gaseous phase, 159. in the gaseous phase, which of the following diatomic molecules would be the most polar? All right. So what we need is difference in electronegativity. Change in electronegativity. That will determine the polarity of the diatomic molecules. And since there are only two atoms, then if they have a polar bond, the whole molecule is polar. So let's look at them. CSF, B is CSCl, C is NaCl, D is NaF, and E is LiF. Okay. The most electronegative atom in this bunch is fluorine. All right. So if you toss in a coin between cesium fluoride and cesium fluoride wins. Right? Sodium fluoride wins. So those two are out. We have to compare these others. Right? So where are they on the periodic table? Well, fluorine obviously in the upper right-hand corner. But where's cesium? Cesium is way down here in the left. Whereas sodium is up here. Right? Go up a period, your electronegativity increases. Right? So the very lowest electronegativity is down here in the lower left-hand chart against fluorine in the upper right. So I think it's a fairly easy answer. That has the most polar bond. Now, technically speaking, we usually don't discuss polarity for ionic compounds because the electrons are completely transferred. It's just electrostatic attraction. But we're going to stretch the definition a little bit and say which one has the most polar bond. Well, the one with the largest difference in electronegativity. And since all of these are metal nonmetals anyway, we don't have any choice. Cesium fluoride, A, is the answer. All right. And we still got a couple of minutes. Let's see if we can make any sense of this one. 176. Okay, we've got these three molecules. Let's see, 1, 2, and 3. Remember these? It's known as cyclic compounds. And remember, at each one of these junctions is a carbon. Right? And let's put in our double bonds. All right. So why don't we put a double bond here and here and here? Well, because we left out the hydrogens too. There's one hydrogen here, here, and here. So that means 1, 2, 3, 4. 4 times 2 is 8 electrons. Carbon has its octet. But here we have 1, 1, 1, 1. Here we have 2 hydrogens. And here we have 2 hydrogens. So by the same token, there's 1 there, 2 here, 2 there, 2 there, and 2 there. So if you count them up, this is C6H6, 6, 6. This is C6H8, right? 1, 2, 3, 4, 5, 6, 7, 8. And this one should be C6H10. 1, 2, 4, 6, 8, 10. Okay. Now what's the question? Which molecules have equivalent carbon-carbon bonds throughout the molecule? Equivalent how? Well, usually when we say equivalent, we mean equivalent in bond length and bond strength. So which ones would be equivalent? Well, if we look at just the way they're written, the double bonds should be shorter and stronger. And in these molecules, they are, because they can't be spread out. They can't be delocalized. You can delocalize over this right here, right? But these are different. Or you could delocalize over these, and all of those would be different, right? So those have not equivalent bonds. This one, you can delocalize over the entire molecule, and every bond is the same length and the same strength. That's why when we write this one, which is benzene, very often we write it like this to show that every bond is equivalent. Otherwise, with the valence bond theory, you have to write the resonance structure here, which you just move this bond over here, and that one there, and that one there, and that one. There's only 2 resonance structures for benzene. But for the molecular orbital model, doesn't matter. All bonds are equivalent. All bonds are molecular, actually. They're not derived from atomic. How about the electronic configuration of a particular diatomic species is that, right? This is molecular. What is the bond order for this species? I should have just said compound. 177. Remember what the bond order is. Right? Bond order equals the bonding electrons minus the anti-bonding divided by 2. So we just need the number of bonding electrons, which would be, right, there's 2, 4, 8 total. Anti-bonding would be the stars, which would be 2 and 2 minus 4. So 4 from 8 is 4, divided by 2 is 2. Okay, so the answer to that one is D. How would we interpret that bond order? Well, typically we say a bond order of 2 means a double bond. Bond order of 1 is a single bond. Bond order of 3 is a triple bond. But in molecular orbital theory, it's not a one-to-one relationship between valence bond and molecular orbital. The bond order does tell you the strength of the bond. So the higher the bond order, the stronger the bond. But we're not limited in the molecular orbital theory to unit increases in bonds. We don't have to say single, double, or triple. The bond order can be fractional. Right? We could have 1/2 bond, or we can have 0. Or we can have 2.5. Right? If we have 0, or if we invent something that gives us a negative bond order, we know that there's no bond formed there. It's impossible. Okay. Let's see. This is page 9. This might be a good place to stop. So let me make a note for myself. Since I don't have a hard copy for this thing, we're on 180. Let me just make a note. Maybe I'll print myself a copy of this thing. I won't change the numbers, though, because we've already started. So 180 is where we pick up Wednesday.